Section 8.8 Taylor series. In this section, we seek to represent a function as infinite series. Recall from section 8.7 that a series can be differentiated term by term or integrated term by term in the interval of convergence of the original series. For example, if we differentiate the series sigma 3 to the power of k plus 1 divided by 2k factorial multiplied by x minus 4 to the power of k term by term, we get sigma 3 to the power of k plus 1 divided by 2k factorial multiplied by k multiplied by x minus 4 to the power of k minus 1. By using the power rule for differentiation, if we integrate the given series term by term, we get 3 to the power of k plus 1 divided by 2k factorial multiplied by 1 divided by k plus 1 multiplied by x minus 4 to the power of k plus 1 plus c. We can use the procedure of differentiating term by term a series to prove that the series sigma 1 over k factorial multiplied by x to the power of k represents the function exponential of x. Differentiating this series gives 1 divided by k factorial multiplied by k multiplied by x to the power of k minus 1. We list the terms of the initial series and the resulting series. As they are the same series, it means that the derivative of the given series equals itself, so the given series must be the representation of exponential of x. The following theorem will help us to find the representation of a function as power series. If fx can be written as a power series, it must be fx equals sigma k equals 0 to infinity of the kth derivative of f as c divided by k factorial multiplied by x minus c to the power of k. We can list the terms of the series fc plus f prime c multiplied by x minus c plus f prime c divided by 2 factorial multiplied by x minus c square plus f triple prime c divided by 3 factorial multiplied by x minus c to the power of 3. This is the Taylor series for f when c equals 0. This series is called the Maclaurin series for f. Find the Maclaurin series for fx equal exponential of x. To find the Maclaurin series, we have to compute to the kth order derivative of exponential of x at 0. Since they are all equal to exponential of x, their values at 0 are all 1. Substituting in the formula of Maclaurin series gives fx equals sigma k from 0 to infinity of the kth order derivative of f at c divided by k factorial multiplied by x minus c to the power of k. C equals 0, so it is simplified as sigma k from 0 to infinity 1 over k factorial multiplied by x to the power of k. The next example is to find the Maclaurin series for fx equal cosine of x. We recall the form of the Maclaurin series. Since cosine of x does not have the same derivative of all order, we should express them term by term. First, we compute f0. It equals cosine 0 equals 1. Then we find the derivatives at 0. The first derivative is minus sin x. Its value at 0 is 0. The second derivative is minus cosine x. Its value at 0 is minus 1. The third derivative is sin x. Its value at 0 is 0. From the fourth order, the derivative comes back to cosine x and the cycle repeats. So cosine x equals 1 plus 0 minus 1 over 2 factorial x squared plus 0 plus 1 over 4 factorial x to the power of 4 plus 0 minus 1 over 6 factorial x to the power of 6. This series can be written in compact form as sigma k from 0 to infinity of minus 1 to the power of k divided by 2k factorial multiplied by x to the power of 2k. Next, find the Maclaurin series of fx equals sin x. We recall the form of the Maclaurin series. Since cosine x does not have the same derivative of all others, we should express them term by term. First, we compute f0. It equals sin 0 equals 0. Then we find the derivatives at 0. The first derivative is cosine x. Its value at 0 is 1. The second derivative is minus sin x. Its value at 0 is 0. The third derivative is minus cosine x. Its value at 0 is minus 1. From the fourth order, the derivative comes back to sin x and the cycle repeats. So sin x equals 0 plus x plus 0 minus 1 divided by 3 factorial multiplied by x to the power of 3 plus 0 plus 1 over 5 factorial x to the power of 5 plus 0 minus 1 over 7 factorial multiplied by x to the power of 7. This series can be written in compact form as sigma k from 0 to infinity minus 1 to the power of k divided by 2k plus 1 factorial multiplied by x to the power of 2k plus 1. Until now, we have known that if a function is written as a series, it must be fx equals sigma k from 0 to infinity of the kth order derivative of f at c divided by k factorial multiplied by x minus c to the power of k. This series can be expressed term by term as fc plus f prime c multiplied by x minus c plus f prime prime c divided by 2 factorial multiplied by x minus c squared plus f triple prime c divided by 3 factorial multiplied by x minus c to the power of 3. The series looks like a polynomial in x minus c. Using this theorem, we have found the Maclaurin series of the following functions. Exponential of x equals sigma k from 0 to infinity of 1 divided by k factorial multiplied by x to the power of k. Cosine x equals sigma k from 0 to infinity of minus 1 to the power of k divided by 2k factorial multiplied by x to the power of 2k. Sin x equals sigma k from 0 to infinity of minus 1 to the power of k divided by 2k plus 1 factorial multiplied by x to the power of 2k plus 1. Now we will apply this series to solve some interesting problems. The first problem is find the sum of the series sigma k from 0 to infinity of 2 to the power of k divided by k factorial. We can verify that this series converges by ratio test. But what is this sum? Recall that exponential of x equals sigma k from 0 to infinity of 1 divided by k factorial multiplied by x to the power of k. The given series can be obtained by replacing x by 2 in the above formula. So it converges to exponential of 2. By expressing a function as a series, we can explain the mystery under L'Hopital's rule. Y is lim when x tends to 0 of sin x divided by x equals 0. We write sin x as x minus 1 divided by 3 factorial multiplied by x cubed plus 1 over 5 factorial multiplied by x to the power of 5 plus etc. Dividing by x gives 1 minus 1 over 3 factorial x squared plus 1 over 5 factorial x to the 4th plus etc., which tends to 1 as x tends to 0. By modifying the Maclaurin series for some simple functions, we can obtain the Maclaurin series for more complex functions. The following example illustrates the procedure. Find the Maclaurin series for fx equals x cubed multiplied by cosine 4x. We have found that cosine x equals sigma k from 0 to infinity of minus 1 to the power of k divided by 2k factorial multiplied by x to the power of 2k. Therefore, by replacing x by 4x, we obtain x cubed multiplied by sigma k from 0 to infinity of minus 1 to the power of k divided by 2k factorial multiplied by 4x to the power of 2k. Separating the coefficient and the power parts, we get x cubed multiplied by sigma k from 0 to infinity of minus 1 to the power of k divided by 2k factorial multiplied by 4 to the power of 2k multiplied by x to the power of 2k. Multiply x cubed with each term in the series. It results in sigma k from 0 to infinity of minus 1 to the power of k divided by 2k factorial multiplied by 4 to the power of 2k multiplied by x to the power of 2k plus 3. Find the Maclaurin series for the integral of exponential of x squared dx. In fact, it is impossible to find an antiderivative of exponential of x squared as an algebraic or transcendental function. So we can apply series method here. We found that exponential of x equals sigma k equals 0 to infinity of 1 divided by k factorial multiplied by x to the power of k. Therefore, by replacing x by x squared, we obtain the integral of sigma of 1 over k factorial multiplied by x squared to the power of k dx. Separating their coefficient and the power parts, we get sigma of 1 over k factorial multiplied by x to the power of 2k. Integrating the series term by term, it results in sigma 1 divided by k factorial multiplied by 1 divided by 2k plus 1 multiplied by x to the power of 2k plus 1. Find the Maclaurin series for 4 divided by x sine of 5x to the 4th. We have found that sin x equals sigma k equals 0 to infinity of minus 1 to the power of k divided by 2k plus 1 factorial multiplied by x to the power of 2k plus 1. Therefore, by replacing x by 5x to the power of 4, we obtain 4 divided by x multiplied by sigma of minus 1 to the power of k divided by 2k plus 1 factorial multiplied by 5x to the 4th to the power of 2k plus 1. Separating the coefficient and the power parts, we get 5 to the power of 2k plus 1 multiplied by x to the power of 8k plus 4. Multiply 4 divided by x with each term of the series. It results in sigma k from 0 to infinity of 4 multiplied by minus 1 to the power of k divided by 2k plus 1 factorial multiplied by 5 to the power of 2k plus 1 multiplied by x to the power of 8k plus 3. Find the Maclaurin series for 1 divided by 1 plus x squared. We have found that 1 divided by 1 minus x equals sigma k from 0 to infinity of x to the power of k. The given function can be written as 1 divided by 1 minus x squared. Therefore, by replacing x by minus x squared, we obtain sigma of minus x squared to the power of k. Separating the coefficient and the power parts, we get sigma of minus 1 to the power of k, x to the power of 2k. Find the Maclaurin series for the inverse tangent of x. Notice that the given function can be written as the integral of 1 divided by 1 plus x squared. We have found that 1 divided by 1 plus x squared equals sigma k equals 0 to infinity of minus 1 to the power of k multiplied by x to the power of 2k in the previous example. Integrating the series term by term, we get sigma of minus 1 to the power of k divided by 2k plus 1 multiplied by x to the power of 2k plus 1. From this result, we can find a series representation of the number pi. Notice that inverse tangent of 1 is pi over 4. So, pi equals 4 multiplied by sigma k from 0 to infinity of minus 1 to the power of k divided by 2k plus 1, which can be expressed term by term as 4 multiplied by 1 minus 1/3 plus 1/5 minus 1/7 plus etc. A famous formula in complex analysis is Euler's formula. This formula gives a representation of complex number as the exponential function exponential of ix. By replacing x by ix in the series we have found for exponential of x, we obtain exponential of ix equals sigma k from 0 to infinity of 1 over k factorial multiplied by ix to the power of k. Using the fact that I squared equals minus 1, this series is written term by term as 1 plus ix minus 1 divided by 2 factorial x squared minus I multiplied by 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th plus I multiplied by 1 over 5 factorial x to the 5th. By separating the real part and the imaginary part, we realize that they are the series for cosine and sin x, respectively. So we have proved Euler's formula. Exponential of ix equals cosine x plus I sin x. When x equals pi, we obtain the identity exponential of I pi equals minus 1. This is the end of section 8.8. Thanks for watching.